Let's dive into some of the winning solutions for a recent Kaggle competition. This Kaggle competition was about retrieval using Gen AI technologies. And while everybody's use case is going to differ a little bit, I think some of the patterns that they found, some of the techniques they found will be useful to anybody that's working on retrieval, RAG type use cases like that. Now, the competition itself, I'm not going to go into the specifics of the competition. It's a pretty kind of detailed competition around looking at misconceptions in mathematics. There's lots of details here. What I want to point out is that there's thousands of people working on this, and they've shared their solutions, their insights for what works. And I find these reads fascinating because what these people have done is they've spent the last few months working, running hundreds of experiments to figure out what retrieval, what tools work the best to solve this problem. Now, this doesn't always help you with your problem, but a lot of times in my experience, what Kaggle competitors learn, the tricks they use, the techniques, the experimentation, often we can reuse a lot of that in our own research and our own problems we do. Now, for the first place solution in this competition, wrote an extremely detailed and excellently presented summary. So I'm going to refer you to that. I'm going to share with you my distilled thoughts from that summary. I've thrown this together in terms of going through what they've wrote and how it could be useful to all of us and put it into this visualization. So I'm going to use this as a little bit of a roadmap, and we'll refer to the blog post as well and go through this. So this was a retrieval use case. And so the first thing is used a mixture of retrievers. So often we think about picking maybe one retriever, going to the multi-text embedding leaderboard, picking out one of the top retrievers here. Like a lot of Kaggle competitions, they found that ensembling, right, using multiple models gives you a little bit of boost of performance. And you can see this in among other competitors that might have just used one model, or as is the case here, they also fine-tuned the model as well that gave it a boost. And if you look through the solutions, you'll see that both of these techniques gave some improvement here. Now, the retrievers they used here are the ones specified here. You'll see they're kind of on the bigger side of retrievers. They fine-tuned these with LoRA. Now, the way these retrievers worked is pretty interesting. What they did is, and it's detailed here in the retriever section, but what they did was they used the retrievers to get the top 32 results. Now, after that, what they said is, hey, if any of the results are within something like 0.06 of the number one, so if you have other results that are really similar to the top result, well, let's bring those in as well, up to a max of 64. And this is often what you want to use retrievers for, is just going from lots of different data that you have down to a smaller subset. And that's what they did here. And these retrievers will bring anything back to from 32 to 64 results. Now, once the retrievers have that, another very popular technique for people to use is a re-ranker. Now, a re-ranker is going to go with that big list that we have, that 64, and re-rank those to tell us which is the most important. Re-rankers are typically more heavyweight models. They take a lot more compute to run, so it's something that it's too much to run across our entire data set, but if we only have a smaller subset, they can do much better in terms of giving us a final ranking than just relying on retrievers. So you'll see throughout the space, lots of folks using rankers. What's interesting here is the strategy that they used for rankers, where they used 3 different rankers of 3 different sizes and cascaded them, where the first ranker was a Quen 14b, and this was used pointwise re-ranker. So it just looked at each individual item and ranked them to figure out which ones were in the top 8. After that, the next ranker was a little bit bigger capacity, and it got to the top 5. Now, the last re-ranker was not a pointwise, but a listwise re-ranker. So it takes an entire list of the top 5 and then tells you which order they should be in. So there's actually 5 outputs that come out of this re-ranker model. Now, if you're curious on what is the performance improvement out of these re-rankers. They've shared that here in the diagram. You can see a similar cascade thing. And we can see here the steady improvement by using these multiple re-rankers. Now, most of us aren't going to use multiple re-rankers in this, but I just want to highlight this to you to show you how using multiple models, going through careful experimentation, you can find ways to pick up a little bit of extra lift in your models. Now, I mentioned earlier that these models were fine-tuned. So they were fine-tuned with the training data that came, but they also generated synthetic data as well. And they generated about 10,000 examples of synthetic compared to the original 2K of training data. Now, as they go through here, the synthetic data that they created, they initially started with simple prompt. They found out that that synthetic data just wasn't covering everything well enough. They did some clustering analysis, figured out what are the groups that we need to have covered in our synthetic data to have good coverage to cover all the types of use cases we have. And then they wrote a better prompt. One of the things they wrote here is they used Anthropic's meta prompt guide to help write a better prompt. I'll link that and share that too. That gave them a much better detailed prompt, and it started to allow them to hit that synthetic data in those areas that they needed it, so that their synthetic data was much better than where they started with. Now, with that synthetic data that they pulled in, and they've shared the prompts here with it, the next step was, well, you have a lot of synthetic data. Which of the synthetic data should you use? And this is where they used an LLM as a judge to review all that synthetic data to see, hey, let's keep the high quality synthetic data. Let's drop the low quality data. This is an easy technique that any of us can use. Most of us should be using synthetic data for thinking about fine-tuning models. There's a lot of details in here about how they fine-tuned with LoRA and different learning rates. I don't want to dwell on that. One interesting technique they used here to enrich in their training data was they used chain of thought data as well, additional training data. So they asked a Claude model, they took the examples, they asked a Claude model, hey, give me a detailed reasoning for how you would solve this problem. And then they took all those reasoning pieces and stuck them in to the training data for that re-ranker model. And what that does is it helps when they're doing predictions to see, hey, yes, we might not have all the pieces, but does it make sense? Is it following the same type of logic that we've seen in other places? That actually gave a little bit of a lift by using this extra chain of thought data. And then they share in here in the paper, you can see exactly how much lift they got through by using the extra chain of thought. But that just shows you some of the smart ways that you can improve your synthetic data is by adding other original pieces in there as well. You can see here they've shared the performance of their individual retrievers. They've also shared the different types of re-rankers. They have their listwise re-rankers as well as the pointwise re-ranker as well. Here's the list. Oh, that was a pointwise. Here is the list one here. And you can see here that they've brought in those chain of thought examples as well to use with this. All right. The last couple things I want to leave you with is fundamental techniques that we always need to be thinking about. They used quantization. There's a lot of quantization libraries out there. I saw different competitors use some different ones out there. Here they use the Auto AWG. One thing they highlight, and it's remember for us to take into consideration, is when you're using quantization, you're going to have a little bit of performance degradation because there's trade-offs, right? You're quantizing, you're using less of that memory space for that. But what you can do is you can help calibrate it. Use a calibration data set. And they used a calibration data set for that quantization so it knows what to quantize and what not to. That gave a little boost in the overall performance compared to non-calibrated as well. So that's a strategy you should think about. Of course, for validation that they used a group k-fold. So this is the fundamentals of data science like that. All of our training data isn't entirely independent of each other, thinking about where there's patterns. So using the group k-fold approach like that gives you a little bit of better validation. And in the case of things like Kaggle, you really don't want to overfit. This has been a quick summary of this. Go read the full detail of this. They've shared all the code that they've used for training this model for inference. This is the first place solution. It is a bit more complex solution like that. I'd also urge you to go take a look at some of the other solutions, including some of the simpler solutions, some of the efficiency solutions. All of these are touching upon how to do good retrieval. So they're all going to be about techniques for how to use a retriever, how to use a re-ranker, how to quantize, use fine-tuning. All techniques that everybody should be comfortable with that's working in the Gen AI space. All right, thank you all.